Yes, I am retired since 10 years ago, perhaps, and I continue to do mathematics. And about polynomials, Newton methods, and numerical algebra, and numerical method to approximate roots of univariate polynomials and systems of analytic function. And today I speak about the Ilieff-Sendov conjectures. It's a very difficult conjecture, and this conjecture has been stated by a Bulgarian mathematician named Sendov, Belgovat-Sendov, exactly. And first I speak about this image. This image is the dynamical study of Newton methods for an univariate polynomial, which has, I believe, 14 or 100 roots. I don't remember exactly. And there is a property, very important property, which said all root of univariate polynomial is connected to the infinity when we study Newton methods. And this property is not satisfied for a system of polynomial or system of analytic function. And we study the Newton method. Newton method, it's a map. The formula is z minus p de z on p prime of z. And p prime of z, it's at the denominator, and the root of p prime of z, it's a difficulty to work with the Newton method. It's a classical property, and perhaps you know this property. And the property which connects the root to the infinity, it's very important and to approximate the root. And this it is a study of dynamical property of Newton method. And how it's related to the Ilieff-Sendov conjecture. It's right of the Sendov conjecture because the Sendov-Ilieff conjecture said all univariate polynomial was the root as in the unit disk. It is easy to, when you have a general univariate polynomial, it's easy to do that all the roots are in the unit disk. And then it's true that the distance between the root of the polynomial and the root of its derivative is less than 1. Yes, I explain this in 5 minutes. In all these P, it's a polynomial of degree d. Its roots are z1, etc., zd. The root of p prime, the derivative, are zeta 1, etc., zeta d minus 1. And on this picture, there is Sendov is here, and Ilieff is here. And it's a picture of Bulgarian groups in the 16. Okay. First, the conjecture holds when the polynomials is zd minus 1. It's an example, and the derivative is in 0 and, the derivative and the root are the root of unity is here. Also, when the polynomial is zd minus z, you have the root in red and the root of the derivative in blue. And in a certain sense, there's two polynomials can be considered as extremal polynomial for its problem. But I don't develop this aspect today. It's important property, but I don't develop. The conjecture holds when you do numerical experiment. For instance, d equal 10, etc. And you can see when the degree grows, the root of the derivative in green or blue here goes to the root, very close to the root. Here, we don't see the roots and the roots of the polynomials, the root of the polynomial and the root of its derivative are very, very close. Okay. Experimentally, the conjecture holds for random polynomial. Here, random is with normal law. Okay. Okay, for instance? You have question? No? What is the strategy to prove this conjecture? The strategy is to suppose we can suppose there is a root on the x-axis. It's very easy to do like that. You can make a rotation. And with rotation, specific rotation, the root of the derivative and the root of polynomial lies in the unit disk, and the derivative lies also in the unit disk. It's a simplification to prove the conjecture. Next, we suppose that the roots of the derivative lie in this lune. Okay. And the goal is to find the contradiction. But find the contradiction is not so easy. Okay. There are other strategies. Perhaps I develop this at the end. Okay. To prove this conjecture, we need to know on the subject, special subject, it is the geometry of the root of polynomial. What is geometry of a root of polynomial? Geometry of the root of polynomials, of polynomial roots, is the links between the root of the derivative and the root of polynomial. When you consider a univariate polynomial and you consider the real roots, you know that by, for instance, Rolle theorem, that between two real roots, there is at least a root of the derivative. Okay? And it is the geometry of real root are very easy. It's given by Rolle theorem. But in the complex case, is not so easy because you have seen here between two roots there is no root of the derivative. And these do that the conjecture is complicated. And what is the equivalent of the Rolle theorem in the complex case? At my sense, there is, in the literature, there is a tentative to develop a Rolle theorem for roots of a polynomial in the complex case. But at my sense, the result, which is the equivalent of Rolle theorem in the complex case, is this result. It's this result. It's a theorem proved by Gauss and Lucas. It's a Gauss-Lucas theorem. Perhaps you know these theorems. And this theorem is very beautiful because he said the roots of the derivative are in the convex hull of the root of the polynomial. I prove this theorem, and habitually there is a root by contradiction, mathematical contradiction. But when you do proof by mathematical contradiction, you don't know exactly what is you don't know, you don't it sorry, it is not a constructive proof. And here I give a constructive proof. Okay, the goal is to prove each root of the derivative is a linear combination, a convex combination of the root of the polynomial. And convex combination, it's this zeta right as like that. Oh, sorry. And the interesting case is when zeta is different of the root of the polynomial at this stage, at this step here. And the fundamental relation is this relation, like that. When you divide p prime zeta by p de zeta, you have this equality. And from this relation, it is very easy to write the root of the derivative like that with this coefficient. And the sum of this coefficient is exactly 1. You have a constructive proof of this theorem. In the manual, it habitually the proof is proved by mathematical contradiction. Okay. You have question? No? It's clear? Okay. It's very important because you see it's the first link between the root of the polynomial and the root of the derivative. Okay? A remark. If you examine this experiment, you see that the root of the derivative in green are not in the convex hull of the root. Why? You have an answer? Yes, because there is numerical error. And you can obtain exactly the property of the convex hull if you grow the digits to perform this computation. And if you grow the digits, you obtain exactly the property of the convex hull. Okay. There is two other results. The first is two other results which are connected. The first said, if you consider Z1, on the x-axis, and you consider C between 0 and Z1, like that. The result said there exists a circle around Z1 like that. The evaluation of polynomial in C equal there exists Z in this circle, in this disk, small disk, such that the evaluation of the polynomial in Z equal the evaluation of the polynomial in C. Is a very important property. And the result states like that. When you consider delta equals Z1, P Z1 is the root of P, and the disk of diameter this segment as the root of P delta minus omega. And you applied this result as this situation. Okay. And there is a corollary of this result which permits to localize the root of the derivative with respect to the root of the polynomial. Okay? Yes? Z is in this Z. D is a degree. D is a degree. Yes, no. Good question, good question. D is a degree. It's D multiplied D times P delta minus omega. Okay. It's very important property, and this property, I don't believe you know this property. I don't remember exactly, but I think it's Laguerre theorem. But I need to verify because my memory is not strong. Okay. I can continue? It's okay? I don't it's the result said that there exists Z like that. It's a result. Okay. The result said there is a root of P delta minus omega. And you apply this result as this situation. And you obtain this. Okay? Omega equal PZ. And there exists a root for any omega different of P delta. There is a root of this polynomial for all omega in different of P delta. Omega is a complex number. Okay? And you can consider you have a z like you can consider omega equal to p de z. It's the result like which said that. J'entends pas bien. Ah! C is between 0 and Z1. It's for any omega different the P delta. And you can consider, I can consider Z between, C is given. C is given between 0 and Z1. Okay. Sorry. Okay. And the link previous result is like that. Suppose you have two complex numbers such that P A, evaluation of P on A and evaluation of P on B are equal. Okay? Then the perpendicular bisector of the line segment AB intersects the convex hull of the root of P prime, of the derivative of P. Okay? And the figure is like that. You have C, you have Z. P de C equal P de Z. Then, the perpendicular bisector intersects the convex hull of the root of the derivative. In this case, I am suppose that the root of the derivative are in this lune. It's a strategy to prove the theorem. And the consequence, if you have a root here and all the derivative in this lune, then you have the perpendicular bisector intersects the convex hull of the root of the derivative. It's a very, very good application of this result to attack the conjecture. Why? Why? Because this situation is not possible. You have two roots in red. Suppose you have all the root of the derivative on the left, it is not possible. You need to have a root also on the right. Okay. Example. Application, sorry. If you suppose all the root of the derivative are in this loon, okay? Then there is no root in this set, because if you consider a root here, then the perpendicular bisector does not intersect this loon. And you need to consider the perpendicular, the line segment here and the line segment here, which are orthogonal as these two segments here. And you deduce that there are no roots in these sectors. Okay? And the same reasoning said you have no root first on the line segment between Z1 and the origin. Okay? It's okay? Because if we consider a root here, the perpendicular bisector does not intersect the loon. Consequently, there is no root on the x-axis between 0 and Z1, the root of P. It's okay? Yes? I repeat? Yes. I repeat differently. Here you have a root of P. And you consider the line segment between the origin and Z1. Okay? And you consider C. The perpendicular bisector of the line segment CZ1 does not intersect the loon, because the perpendicular bisector is like that. Sorry. Okay? Consequently, C cannot be a root of P. Okay? No. The result said if C is the root of P, P to C equal P to Z1 equals 0, then the perpendicular bisector of the line segment CZ1 intersects the loon, but is not possible in this case. Consequently, C is not a root of P. And the same reasoning by the same reasoning, you can prove that this set here has not a root of P. I don't, but it's you consider a line segment and you remark the perpendicular bisector does not intersect the loon, and you can construct these two curves and the interior, and in this interior there is no, there is no root of p. Okay. Consequently, if the root of the derivative are in the Lune, in this set, you have root perhaps of p, but not in this set and not in this set. And in this manner, you can find analytic estimates of the distance between two roots of p, and perhaps estimate between a root of p and a root of the derivative. And it is the goal to prove the conjecture. This strategy said more on the geometry of the root of polynomials. Okay. You have question? Yes.
You talk about this perpendicular line.
Yes.
You used the previous theorem, and there was a circle with another possible root in the circle. Like we don't.
You have. It's possible, for instance, to have a root here, a root of polynomial. It's possible here, not possible here, not possible here.
And the reason why it's not possible is because you draw the perpendicular line.
Does not intersect the Lune.
And the center of the red circle.
Yes.
Okay, but in the previous theorem, you didn't have just the center of the red circle, there was also a small ball around it.
Ah, yes. There is, yes. I speak about in the slides later, because when you have a complex where the polynomial is not does not cancel, there exists a ball around this complex where the polynomial has no root. Yes, and later I explain this, and I will give some estimate on the radius of this disk. Okay. And to do that, I think we use a result named Rouchet theorem. Another Laguerre theorem. And a quantity which is important is the center of mass of this quantity. And it's defined like that. Z minus D, D is the degree, P Z on P prime Z. Is close to the Newton method. In the Newton method, Z minus P de Z on P prime Z. Here you add D for the center of mass. Okay, and P prime Z on P de Z equal to this quantity. When you have seen, as we have seen in the Gauss-Lucas theorem. Okay. And there is a property is to link the center of mass with the derivative and the second derivative of the polynomial. It's very easy to prove this, and I don't insist, because I speak about like that because I will do an attempt of proof of the conjecture in the later. And the attempt of proof use this expression. You have the proof here, and the proof is a very simple computation. Okay. Sorry, n is d. Sorry. Good remarks. N is d. I take d because d like is degree, en can be also the degree of polynomial, but generally is a number of variables. And I prefer use d like degree for the degree, and n for the number of variables. Okay. Sorry, there is a condition to localize a critical point. Consider Z naught a simple root of P de Z. If you have if this inequality holds, then the derivative has at least a root in the disk centered in Z naught and radius 1. It's very simple to prove this conjecture by mathematical contradiction. You write the expression of the derivative. Sorry, perhaps I don't said that the univariate polynomial is monic. That is to say, the coefficient of xzd is 1. It's a monic polynomial. And as p is a monic polynomial, the expression of p prime, the derivative, is like that. And this p second on p prime equal this expression. And if you suppose there are not root of the derivative in this disk, then you have this inequality, and this inequality in fact gives the contradiction here. Here is D, is not N, is D. And this is not possible. Yes? Oh, no. Okay? A first result in direction of the proof of this conjecture. You consider a root on the unique circle. And if you have that, then there exists a root of the derivative in this disk centered in you have a root of the derivative satisfied this inequality. I don't the proof is here, but I don't explicit the proof. It's very, very easy. The important is if all the zk are in the unit circle, then the Ilieff conjecture holds. It's a generalization of this situation here. Okay? Because now you can suppose any zk on the circle and you have the Sendov conjecture. And the Sendov conjecture is a theorem. Okay. Okay. It's the case very simple where the conjecture holds. After, the question is the conjecture holds for degree 3, 4, 5, etc. And in fact, we can prove by very technical proof that the Ilieff-Sendov conjecture holds for degree between 3 and 8. And it's an open problem for degree 9, 10, etc. And for 9, it's very, very, very difficult. Okay. And it's based asymptotically, the conjecture holds because you have this property. Each disk centered in a root and radius, this radius contains the root of the derivative. And as this quantity converges to 1 when D is very large. And the conjecture holds when D is very large. Or close to. Because this radius is greater than 1. Okay. Hence, we have the situation, the conjecture holds for certain polynomial, The conjecture holds when the roots are certain distribution. For instance, are the root on the unit circle. And the conjecture holds when the degree is less than 8. For degree 2 is evident. Okay. An attempt of proof, but it's false. Why? Suppose that the center of mass of Z1, ZD minus 1 with respect ZD satisfied this inequality. I remember the center of mass. The center of mass is this point. Okay. By Laguerre theorem, if the Laguerre theorem is satisfied, then the conjecture holds. Okay, the Laguerre theorem said, I remember, where is the Laguerre theorem? It's okay, is here. No. Laguerre theorem, okay, is here. If this inequality holds, the conjecture holds. Okay. I write this expression, and with this assumption, immediately you can prove that. And the disk centered in ZD and radius 1 contains the root of P primes. And the conjecture is proved. But this assumption is not always satisfied. Damage. Example, if you can a root here, here, and here, you have the derivative and zeta, the center of mass, does not satisfy this equality. Okay. Now I speak about Rouchet theorem because Rouchet theorem said how many roots of the polynomial are in a certain disk. And Rouchet theorem is very general. It's holds for univariate in the univariate case, but also for multivariate case in the for analytic function. And the Rouchet theorem said if on the boundary of a disk, I speak about disk, but you can consider Jordan region, but here I limit my statement about, for disk. If for all points on the boundary of a disk, if you have this strict inequality, then the number of roots of f and g in this disk are equal. And in this statement, each root is contained with its multiplicity. Okay. This theorem is not constructive because here you have for all. And we need to prove. Il reste combien de temps encore? Bon, d'accord. Alors. Ok, je passe alors. Bon, it's possible to have a constructive version of this theorem. I pass. And with this theorem, you can obtain a separation number between to the root. Okay. The first important result for the conjecture is said if the degree is sufficiently large, then the conjecture holds. But we don't know the value of this n. It is a proof, it is a not constructive proof. Okay. The inventory of the progress of the conjecture is like that. Sendov states the conjecture. Here, next, Fels-Rodriguez proof for d equal 3 and 4. Meher-Sharma proof for d equal 5. Borcea proof for d equal 6. Borcea and Brom for d equal 7. And Brom and Xiang prove for d equal 8. And there are three regimes for the conjecture. When Z1 equals 0, when Z1 between 0 and 1, and when Z1 equals 1. And there is the progress of this conjecture in these three regimes. I have 1 minute, 1 minute, one minute, and I finish. And we can essay to construct a counterexample. To construct a counterexample, the strategy is the following. You consider this polynomial. And you have this situation. Here are the derivative of f. Here you have a root of f. And the strategy is to prove that the root of this polynomial are in the 0, 1, in the disk centered in 0 and 1. But this, we can prove this is not possible. And the attempt to construct a contingent is very difficult because we have this example. Thank you for your attention.
So maybe I have questions. So have you worked yourself on this question or something related to this?
I will say that in the progress inventory, for those, the work of Tao is very, very different. Tao, you know Tao, Terence Tao? Yes, perhaps yes, perhaps no. Terence Tao write a paper on the Sendov conjecture and prove the same result of Dego. But he used probability theory and define a law of probability on the root of polynomial and the root of the derivative. And in this way, he proved first in this regime the conjecture hold when Z1 is the root of the x-axis, is small o, little o on this quantity. And he used the work of Dego in this regime, and for the third regime, this regime, he proved this when Z1 is between this and this, the conjecture holds. And the work of Tao is, for me, very, very original compared to the other work, previous work. Sorry. Thank you.